So today I'm going to teach you a technique that can be used to nail certain integrals which have trigonometric functions in them. Now these are called trig integrals. Now I have given three examples of such three trig integrals. If you look at the first one, it's an integral which has sine and cosine only. And one interesting thing is that the power of the sine is odd. So this is the first type of integrals that we will consider, where one of the powers of sine or cosine is odd. Now we look at the second one, that too has sine and cosine, but both powers are even. Now the third one has a secant, and the secant power is even. Alright, so these are three types of integrals that can be nailed using the techniques that we will present today in class. Now once again, as I always tell, before you try the heavy-duty techniques, you must always see whether a simple U substitution will work. That should be your first line of attack, and only if that doesn't work, you should go on to try the others. Now, so let's try with an example where we have a trig integral and a simple U substitution will work. Now let's take a look at this integral. Now, will a U substitution work here? Well, if you look and put u equals sine x here, then this will become u to the 5. Also, the derivative of sine x is cosine x, and that is right there in the leftover part. This means that this will be a good candidate for a u substitution. However, if you have an integral like this, by example 2, then you will see that the same technique will not work, because if you put u equals sine x, well, surely this will become u cube, but the leftover part, which is cosine squared x, does not match with the derivative of sine x, which is actually just cosine x. So the derivative of sine x will be cosine x, but the leftover part has cosine squared x, which is a problem. So that will not work. The u substitution will not work here. You can even try it for u equals cosine x, and you will see that it still will not work. So now here is the method that you can use for this integral. Now you will notice that this is the first type that we described, where we have the integral will have only sine or cosine, and one of the powers, either the sine power or the cosine power or both, must be odd. So only sine and cosine, and one or both of the powers must be odd. Now here is the method. What we do is, we first look at that odd power. So in this case it is sine cube, and what we are going to do is we are going to split the odd power into 2, and we are going to take away one of the sine x's, only one of the sine x's. So sine cube is split as sine squared and sine x, and I will take one of the sine x and then throw it right to the end and reserve it with dx. Okay, so you will notice that what I did was I split the sine cube as sine squared and sine x, and the sine x I threw right to the end, and the sine squared is left here. What about the cosine squared? That is still here. Okay. Now that is step 1. Now step 2 would be convert the remaining even power into the opposite trig using the Pythagorean formula. Now what do you mean by that? Now when we split that sine cube, this is the remaining power of sine. Okay, we split the sine cube, and this is the remaining power of sine, and that is an even power. To split this, to convert this to the opposite using Pythagorean. So what is the opposite of sine? Sine. The opposite of sine will be cosine x. Now can I convert this into cosine x? Oh sure, because using Pythagorean I can write the sine squared as 1 minus cosine squared. If I do that, then this will become a cosine thing. Do we touch this? No. Do we touch this? No. So we will only convert the remaining even power into cosine. So we wrote that thing as 1 minus cosine squared x. And this will remain there. This will remain there. Now we go to the third step. Use u equals the opposite trig. So what do you mean by that? So now the opposite thing that we converted was cosine, right? So we use u equals cosine x. Now you will see why this will work, because if we put u equals cosine x, then du, the derivative of that will be negative sine x, is that thing that we reserved here. Can you see that? The thing that we reserved here is exactly, or up to a negative sign, is the leftover part of the u. So really what we did was we massaged our original integral into a situation where we can actually use a u substitution. So mathematically, we actually are using a u substitution, but we massage the original integral to come to a position that we can use the u substitution, because as it is, the original integral we saw, we could not use the u substitution. Alright, and now we are all set to go. Now we have u equals cosine x, so 1 minus cosine squared x will become u squared, and we have another cosine x here, which is u squared, and the sine x dx naturally is then the negative of du, right, because du is equal to negative sine x. So now you can see that everything is in u. Now how do we evaluate this integral? This is pretty straightforward integral. You can use it using power rule, except that you need to distribute the u squared inside. So if you distribute the u squared inside and take the negative sign outside, you get negative u squared minus u to the 4 du. Now we are ready to integrate. It's a very simple integral now. It's negative u squared integral is u cube over 3 minus u fourth integral is u 5 over 5 plus c. Now we are done now. So the only thing we need to do is to plug back for u. So remember our original u was equal to cosine x. So we now plug in for cosine x. So u3 is cosine cube x, and that's 1/3, and then minus goes inside. The minus minus becomes plus, and then we have u to the 5th, which is cosine 5th, and we have 1/5 plus c, and we are done. So this is our final answer. So once again, to retrace our steps, right, what we did was we looked at an integral which has trig and sine and cosine only, but the sine has, or the cosine has an odd power, and we split the odd power into two and reserved one at the corner and let the other remain, and then we converted the even power that remains by Pythagorean into the opposite, which was cosine in this case, and then we put u equals cosine x, and then that little part at the end just became the du, and then we just use power rule. Now to talk about a second example, let's take I equals integral cosine to the 5x. Now in this one, once again, do we have only sine and cosine? Yeah, we don't have the sine, but still there is a cosine. There is only sine and cosine, and then the cosine has an odd power. So what do we do now? We split the 5 into two pieces, 4 and 1. So 4 and 1, and we throw the 1 into the corner. And then what we do is we need to convert the even power into the opposite. The opposite is sine. So how do we convert the cosine into sine? We know that cosine squared is equal to 1 minus sine squared by Pythagorean, but we have cosine 4 here. So it is 1 minus sine squared, 2 again squared, and the cosine x dx is still there. And now if we use u equals opposite. So what's the opposite here? The opposite here that we converted was sine x. So you put u equals sine x, we have du equals cosine x. And then you can put 1 minus sine squared x will be u squared, and the square on top, and the cosine x dx nicely matches once again with the du. So we have a nice integral here now. This is not hard to integrate at all, except that you need to expand the square out. So how do you expand the square? 1 squared is 1 minus twice the middle term. So that is 2u squared plus then the square of the third term, the second term, which is u to the 4, and now you can continue by using the power rule, the simple integral to integrate using the power rule. So we are almost done here. So now here is the video homework exercise 2, which you should do for tomorrow, just to integrate sine cube x, and you can do it just using the same technique that we used in the previous examples. That's it for now, guys. Have a great evening.